So, of course, yeah, we don't have much of an agenda for today. It's really about just talking about the practice test and about the final and what to be ready for on that. I know there hasn't been much time since I posted the practice final, and I only announced it to you guys on Monday, so you might not have had a chance to look at it. But certainly, with the final being due on May 12th, there's and it'll be posted by Friday, this Friday. We'll do look at practice tests by all means. Send me questions about it if you end up looking at it later. Okay, but at least this will be an opportunity to help you focus on whatever studying you do, like which lessons to really look at. And I indicated for each problem on the practice test which lesson it comes from. So this being a comprehensive final, some old, some new, starting with lesson 9, which is about a non-homogeneous heat equation. So here we have heat equation with a source term of cosine 2 by x, and then our initial condition, and the boundary conditions. What I've seen from time to time is, people see it either on homework or on a test. Occasionally, people solving PE using wrong boundary conditions. Like in this case, we have homogeneous Neumann or type 3 boundary conditions, which would call for a solution having the Fourier series involving a cosine. And now that I've seen someone like a problem like that treating it using a sine series, and things go wrong when trying to handle that. And that's why, because it shows the wrong form of the solution to begin with. So please pay close attention to the boundary conditions. Okay. I'm going to alright. Well, I'm going to do a little editing here real quick. Okay, so now we have someone else here. Oops, something went terribly wrong. This is activating. I'll do a copy paste and won't acknowledge what I copied. Copy. Paste. Okay. Sorry, this editor is being particularly frustrating today. Okay. Okay, now I remember giving this advice for the first test too, but certainly worth repeating. Make sure your solution has the correct form. And what I mean by that is, a couple examples. So if the boundary conditions are following, so in the first case, say the solution is 0 on the boundary, x equals 0. So we're assuming that the domain consists of 0 less than x less than L. So you have a Fourier sine series. A linear combination of sine n pi x over L. And the other hand is du dx. That's equal to 0 on the boundary, so a Neumann or type 3 boundary condition has a Fourier cosine series. That would be a linear combination of cosine n pi x over L. Alright. So for problems solving a heat equation or wave equation on a finite interval, like 0 to L, first thing you do, check the boundary conditions, make sure your solution is the right form. So don't needlessly toss away points by going with the wrong form. All right. So look closely at the boundary conditions and proceed accordingly. Okay. Now, here we have a non-homogeneous PDE. So we focus on the homogeneous version, so tossing out the source term for the time being. See what form a solution has. And you could just follow what I just said, but just for completeness sake, I'm also showing you where it comes from. That these are the ODEs that come about by separation of variables. Apply to this. And I should clarify this reference here. When I say proceeding as in problem 3, what I mean by that is that's from practice test 1. For what? Because that goes into more detail about the separation of variables process. And then this ODE has this general solution. This ODE has this general solution. So a combination of sine and cosine. What combination determine find the boundary conditions? In this case, the boundary conditions are du dx is 0 on the boundary. So this solution of a spatial ODE must satisfy these boundary conditions. So the derivative is equal to 0 at the endpoints, x equals 0, x equals 1. So then, when you go ahead and take a derivative of this and substitute x equals 0 and then x equals 1 and set the result equal to 0, then what we find is that that there is no sine term, and lambda has to be a multiple, an integer multiple of pi. It's worth mentioning that from here we see two possibilities, either a equals 0 or lambda equals 0. So if we look at both of those possibilities, if we go with a being 0, so there's no sine term, you don't have this either, then to make sure that this is 0, then that's where we get the conclusion lambda is equal to an integer multiple of pi. Those are the roots of sine. The other possibility is that lambda equals 0. Well, if lambda equals 0, there's still no sine term, because sine of 0 is 0. You still have this cosine term, but cosine of 0 would be 1. So then your solution is some arbitrary constant. But that is consistent with requiring lambda equals n pi for n equals 0, 1, 2, etc. So here are the functions I mentioned before. For these boundary conditions, it's cosine n pi x over L. In this problem, L is equal to 1. So these are the eigenfunctions. In other words, they're the solutions of this eigenvalue problem. And therefore, your solution is going to be a linear combination of these, where the coefficients in the linear combination come from this general solution of the time problem. So our lambda values are n times pi for each non-negative integer n. So from these two general solutions, for the spatial problem and the time problem, we know which solution is going to have this form. It's just a matter of what are these. And to help with that, now we go to the non-homogeneous PDE that we started with. We take the source term, which is cosine 2 pi x. We expand it in these same functions. Whatever ones we have here, we use down here. Initial data, in this case cosine pi x, also expanded in that form. So we need these coefficients, the Fn and the Bn. And in this case, since the source term and initial data are the same form as these series, we can get the coefficients from here. So we have F2 is equal to 1, and B1 is equal to 1. All over F's, all over B's are 0. So now, if we substitute this and this into the PDE, and we also substitute these into the initial condition, then the result is these non-homogeneous ODEs and these initial conditions. Now, all of these ODEs have the same form, that you have UN prime is minus this positive constant. In general, it's going to be n pi over L squared times UN plus a coefficient from your source term. The initial data for each ODE comes from the coefficients of this expansion of your initial condition from your PDE. So source term contributes this, initial data contributes this. So, and this applies regardless of whether any of these are 0 or non-zero. We have a solution formula for this ODE that's given here. Now, the Fn in general might depend on t. It doesn't in this problem. So for this problem, each Fn is a constant, so you're allowed to pull it out the integral. But if source term depends on t, you have to leave this in here. This is a function of s here. And you have to take it into account when evaluating this integral. For a case where it is a constant, this integral can be evaluated. It just turns out to be this. This is something you can keep in mind. If the problem you're working on has this same form where we have where you know these eigenfunction expansions, and if the source term does not depend on time, you can jump directly to this for each n. You just need to know what the Bn and Fn are. Now, for this problem, if n is not equal to 1 or 2, then both Fn and Bn are 0, so this will become 0. When n equals 1 or n equals 2, then at least one of these terms will be non-zero. So here we put everything together that for n equals 1, we have b1 equal to 1 here, but f1 is 0. And then for n equal 2, we have b2 equals 0, so we don't have this term, but we do have this one. So we have the solution right here. And for all other n, both these source term initial data are 0, so the entire solution is 0. So now we can take all this and substitute them into our form of a solution, our general solution. And we end up with this. So each un of t is multiplied by the corresponding cosine of n pi x over L, and you add them all up. Now, since you're not under time pressure for this, you can decide how you want to proceed. In terms of, like, you can go through the entire separation of variables process if you feel that there's less chance of you making a mistake that way. But here I've also pointed out certain shortcuts that you can take. And as long as you use them in the correct situations, then you can save yourself some time. I still recommend, once you are able to write down a solution, check it. Substitute it into a PDE, substitute it into the boundary conditions, the initial conditions. Make sure they're satisfied. If they're all satisfied, you know you have a right answer. I need a note here about this one. Okay, so this formula is valid for this kind of ODE no matter what. This simplification is valid when Fn is a constant, not dependent on time. Actually, it's really because questions about what happened with this problem? Okay, so the other source term, determine the right functions to expand your solution in based on boundary conditions. Expansion of the source term, expansion of initial data. These contribute source terms to your ODEs, these contribute initial data to your ODEs. The PDE itself, substituting this expansion into the PDE itself, gives you these ODEs to solve. Here's how you solve them. Pair each of these with these eigenfunctions. Again, for your final step, you're using this. So notice everything that happens in this problem, all of this right here, is a consequence of these. This is the most important part of your solution process right here. That once it's boundary conditions determine what functions of x you have here, rely on these to get the ODEs. The ODEs you know how to solve, I've shown you that. Then you return to this to write down your final answer. So This is the key to getting this problem right, these expansions. Next problem, lesson 12. Fourier transform. So in this case, we have a problem defined on the entire real line. So then feel free to use a Fourier transform table, such as the one in the back of the text. So use these rules to take the Fourier transform of your PDE. You can use rules such as from a table to take the Fourier transform of the initial data. So in other words, transform everything, transform the entire problem. The result is an ODE that depends on the parameter omega. That's your Fourier transform variable, your frequency variable. And the initial data for each ODE comes from the Fourier transform of your initial data. So in this case, this is a rule that I used. So we end up with this. Solve the initial value problem. In this case, this is your solution. It turns out to be your initial value times e to this constant times t. That was for heat equations, so it'll be a first order ODE. Then apply the inverse transform. And of course, the problem may say, you can leave this in integral form, so you go ahead and do that. So just be sure to pay attention to what each problem says as to whether an integral answer is okay, or if it says any integrals must be evaluated. So here we're just taking a transform, substituting it into the definition of the inverse transform. It goes in right here. So really, this is what everything worked out. And this is what results. So transform a PDE, transform the initial conditions using appropriate rules. That'll be found in the table. Solve the ODEs, inverse transform. That's the process. This is another separation variables problem, this time for wave equation, lesson 20, which is on the finite vibrating string. Again, note the boundary conditions. In this case, the solution is 0 on the boundary. That means your solution u of xt is a linear combination of sine n pi x over L. So this is what we have in general, but then we get to fill in L equal 1. And in this case, the coefficient is c squared. Remember, c squared. Therefore, in this problem, c is going to be equal to 2. So that gets taken into account here. So for a homogeneous heat equation, a wave equation, homogeneous wave equation, this is your general solution form, where the coefficients Cn and Vn are based on the initial data. So in this case, the Cn coefficients come from a Fourier sine transform of this initial condition, the first one, on u of x0. And then you take the same kind of finite Fourier transform for a second initial condition. That's what you see here. And I've written it this way so that these are Fourier series coefficients. Then you must multiply by this fraction, L over Cn pi. The reason being that when you take a derivative of all this with respect to time, you get this factor that's 1 over this, so Cn pi over L. So this has to compensate for that. All right, so all of this is for a general solution formula for a homogeneous wave equation. When I fill in the particulars, so the coefficient c is equal to 2, we're on the domain 0 to 1. Now, our initial condition, here we have sine x. Sine pi x. Therefore, we have c1 equal to 1. All others are 0. And then for the other initial condition, we have sine 2 pi x. So that means that d2 is equal to 1 times the factor L over c n pi. In this case, n is equal to 2. And c is also equal to 2 in this problem. So thus we get 1 over 4 pi. So now once we fill in about our c's and our d's, then this is our solution. So again, use the boundary conditions. Figure out what your eigenfunctions are. Sine or cosine n pi x over L, or whatever the case may be based on the boundary conditions. For a wave equation, this is your solution formula for the time-dependent, the general solution for a time-dependent portion of a PDE. And then based on appropriate finite Fourier transform of your initial conditions, appropriately scaled for the second initial condition, you can put the whole solution together. But if you go to the trouble of going through the whole separation of variables process for the wave equation, like you're following along what's going on in the less than 20 notes, all right, you get a second order ODE for x and a second order ODE for t. This is the solution of a second order ODE for x that satisfies the boundary conditions. This is the general solution of the second order ODE you get for t, with the unknown constants chosen so as to satisfy the initial conditions. So in this case, I just included the general solution of that so you can jump directly to that. You don't have to go to trouble of what is the solution of the second order ODE. You have that here. So any shortcuts that like I wrote out somewhere in the notes, you can use as long as they fit the situation. Questions about this one? All right, this is the last of the older problems. You saw one like this in the second test. Method characteristics for a first order linear ODE defined on the entire line with this initial condition. So I use method characteristics. So the coefficient of du dx is set equal to dx ds. This is your ODE for x. Here are the initial conditions defined on the x-axis. So x is 0 set equal to tau. That's the initial value in that case. Coefficient of du dt, in this case 1, that's dt ds. And because the initial condition is the x-axis where t equals 0, so that's why, so this is always going to be 0, for our variable s, for initial condition. The initial value for t, in this case 0, that is what goes here. Then, this part of the PDE collapses to du ds, and then you add on the rest of the PDE, so the plus 2u equals the right-hand side of 0, so that's where the ODE for u comes from. Because what we have from these two ODEs is du dt dt ds plus du dx ds. By chain rule, all of this is equal to du ds. And then the initial condition is the initial value for u, but x is replaced by tau, because tau is the initial value of x. So make sure to do that. This ODE for u, the initial conditions are functions of tau. When it's a linear PDE, like this one, you can solve these first. Here, x is equal to its own derivative, so the solution is e to the s times the constant. The constant is the initial value, tau. T turned out to be just equal to s. Here we have this is a separable, actually it's a linear separable ODE that has this solution, it's the exponential with this coefficient times the initial value, cosine tau. So now you actually have a solution, it's just not in the right variables. It's just a function of tau and s, and you really want it to be a function of x and t. So you can use these equations to solve for s and tau in terms of x and t. Well, s is t, so that helps. And then you can use this equation to solve for tau as a function of x and t. So you use this first, use this in here, rearrange this to isolate tau, then you get your formula for tau, plug it in here. And that's where this comes from. And now you're done. So use a PDE, get your ODEs for x, t, and u. Solve the ones for x and t first, then solve the one for u. Then use your ODEs for x and t to solve for tau and s in terms of x and t, substitute into your u, and you have your u in a proper form. That's the workflow there. Any questions on this one? All right, the newer stuff. This is an interior Dirichlet problem, Laplace's equation. Here we're solving on the unit disk. So on the unit circle, the boundary, where r is equal to 1, you have the initial, sorry, not initial condition, boundary condition, sine 3 theta. So these are boundary value problems, there's no time here. And what you can do, you have a general solution formula. You can jump directly to this. Where capital R is the radius, you mind, this is, oh, that's a typo. It should be R squared. Okay. So whatever radius you have here is in the denominator here, so little r over big R is r raised to the nth power. And the coefficients, the an and bn, come from the Fourier cosine and sine transforms of your boundary condition. Now in this case, boundary data is sine 3 theta, so that means that by orthogonality, all the a's will be 0. B3 will be equal to 1. Well, and the happening is your if you take when the boundary data is a linear combination of sines and cosines, like this one, all you need to do is multiply each one by the appropriate power of r. Here, this corresponds to n equal 3, so we multiply by r cubed. Now, be careful. This is on a unit circle in this case, where the boundary data is given. If we were on a circle of a different radius, capital R, that would have to go in here. So for example, suppose the domain of a problem is x squared plus y squared is less than 4. So capital R would be equal to 2, so I would need to have little r over 2 quantity cubed as my as a factor that goes in front of the sine free theta in this case. So be wary of that. That just comes directly from this. So really, you're taking each term in your boundary data, multiplying it by the appropriate power of little r over big R. I'll be sure to fix that typo when I post it. Dang it. So, for interior Dirichlet problem, where a domain is x plus y squared is less than something, this is your starting point. That you know the solution will have this form. Any questions on this one? So I recommend looking at the homework problems for the most recent lessons, just 33 and 34, where your task of solving either an interior Dirichlet problem like this one, or ones I'm about to show you on the annulus or exterior. Because then you can check against whatever answers they have in the back of the book, make sure you're doing it right before you go to the real thing. Here we're an annulus, positive equation on the domain R between 1 and 2. So the inner boundary, U is equal to sine theta. Outer boundary, R equals 2, cosine theta. So in general, for this kind of Dirichlet problem on an annulus, for whatever boundary data you have, whatever radii you have, this is your general solution. As you define the AN, BN, CN, DN corresponding to your boundary data. Now, in general, these are the system of equations that all of your coefficients, AN, BN, CN, DN, have to solve. So you have this one set up for the n equals 0 case, for whatever portion of your boundary data has either a constant term or a natural log term. Just a constant term. So in other words, n equals 0. And then these equations for all other n. So in this problem, on the inner boundary, we only care about n equal 1. The outer boundary, we only care about, again, n equal 1, cosine. So what that tells us is for our system of equations, here are the ones that come from for A0 and B0. In this case, both the right-hand sides are 0. So A0 and B0 are just going to be 0. Now, okay, need to fix this. Okay. So, actually, there's nothing incorrect here, but maybe it should be organized a little differently. So first of all, for G1, the inner boundary, we have sine, yes. But the AN and BN concern the cosine transform. CN and DN concern the sine transform of your boundary data. So what we have here is the a Fourier sine what we have here on the right side is a Fourier cosine coefficient of sine, but that's going to be 0 by orthogonality. So for all n, this right-hand side value will be 0. As for this equation that deals with the cosine transform of the outer boundary data, in this case cosine, we are going to get a non-zero value when n is equal to 1. For all other n, we're still going to get 0. So, so here's what happens for n equals 1. We end up getting 1 because it's plain old cosine s. And here we have the outer radius is equal to 2. So we'll have 2 to the first power here, and 2 to the minus 1 power here, which is where we get the factor of 1/2. So what I'm going to do is I'm going to write these a little differently. Okay, so in other words, I'm going to treat the cases n equals 1 and all over n separately, because they do work out differently. So for n equals 1, this is the system that we get. For all other n, this is the system we get. The right-hand side will be 0. And that's because here we're taking cosine transforms of our inner boundary data, outer boundary data, inner boundary data, outer boundary data. And the only time we're going to get anything non-zero is for n equal 1 and taking the cosine transform of the outer boundary data. So we get this 1 here. Okay, so for n equal 2, 3, and so on, we know that a and b are going to be 0 from this, because there's a system of 2 linear equations, 2 unknowns, with both right-hand side values are 0. Here, we will get something non-zero. Similarly for C's and D's, we're taking the sine transform of the boundary data, inner then outer. So again, if you look at the cases of n equals 1 and all over n separately, C1 and D1 something went wrong here. Okay. C1 and D1 satisfy this system of equations. We'll get a non-zero solution. Give this non-zero value here. For all other n, 2, 3 on up, C and Dn satisfy this system, that's homogeneous, therefore Cn and Dn must be 0. So that's what we get, all 0 values except when n equals 1. So then we can solve this system equation for A1 and B1, that comes from here. And get these values, and then this system for C1 and D1, solve that, work out the algebra, and we get these values. So now, we need to form from our A's, B's, C's, and D's these expressions multiplied by the appropriate cosine n theta and sine n theta. And that's where we get our final answer. So that's a bit more of a pain to work through than the others. Questions about it? this right here, this is where you start. So set up these systems and solve. They come in pairs, solve each pair independently. Once you have those values, your A and B and C and D n, plug them in here, done. So find your algebra in these cases. Last problem. Exterior Dirichlet problem. So Gauss equation for R greater than some value with some boundary data. Now it's the inner boundary domain that stretches off to infinity. Once again, you have a general solution formula, similar to the interior case. Just that now you have raised to the minus n instead of a plus n. The formulas for a n and b n are exactly the same as in the interior problem. So, in this case, we're taking the Fourier cosine and sine series coefficients of our initial data. So because we have a constant term here, that means that A0 is going to be 1. Sorry. Oh, right. So I have to be careful about this. The way these formulas are written, the constant term is a special case because we have this A0 over 2. So we've seen lots of problems where you have your initial or boundary data in a nice form like this. You just read the coefficients off the function. And on the one hand, you still do that with a constant term, except you're not getting A0 from here. You're getting A0 over 2. All right, so that's why the value's doubled. It's because of this. Whereas if sine 2 theta, we just take a coefficient. Within the boundary data, that's 1, so B2 is equal to 1. It would have been different if I had defined A0 to be 1 over 2 pi times this integral, but it's a convention to not do that so that all of these ANs have the same definition as opposed to n equals 0 being a special case. So just be careful about that. And once again, the terms in your boundary data are just being multiplied by the appropriate expression involving R. In this case, little r over the radius of your domain, capital R, raised to the minus n power. Now, whatever constant term you have, that's just going to stay as is. We see a 1 in the boundary data. We see a 1 in the solution. So whatever constant term is just going to stick around. Okay. Now, actually, you can sort of see that here in the solution formula. That's not multiplied by anything that's a function of R. It's these terms that are multiplied by something involving R. So with the B2 equal to 1, for the sine 2 theta term, we're multiplied by R to the minus 2. Again, when you get to the end, you have an answer, the U of R theta in this case, check it. Go ahead and set R equal to the radius corresponding to your boundary. Make sure that what you get is the boundary data. For these kind of problems, that's the only thing you have to check, because as long as your solution is of this form, for whatever constants, A's, B's, or C's, and D's, it already is guaranteed to be a solution of a Laplace equation. You don't have to worry about that part. Just making sure it satisfies the boundary condition. So really, that's where all the work stems from, because you're already able to use this as your starting point. Okay. I've reached the end. Those, but by now, for most of you who are undergrads, they've already decided which problem will be the one you can skip. But again, you can try to get bonus. You get bonus by trying it anyway. Okay. So, already questions about anything I've covered here? Yes.
Can we look at test 2, number 6? I was wondering if that's going to be on the test. Like something similar to it.
Oh, test 2, number 6?
Yeah, that's a specific question.
Okay. Let's see. Okay, no. Have I opened this in the same app? Oh, it doesn't. Wait. That's weird. Okay. All right, so that's what's up there now. So if I flip to the upper one, it's the same app, but since it's a different window, it's not showing up. Okay. Okay, number 6. Oh, I see. All right.
I wouldn't have to do it if it's not going to be on the test, but I was wondering if there's like going to be like 2 source terms in the like.
Oh, okay. All right. This is not part of this.
Okay.
You don't have to split into 2 problems. Now, something like this is a possibility where your source term has more than one thing. And then therefore you're going to have, in this case, you have like multiple values of n from which you may have a non-zero solution. So yeah, that's a possibility. So I think the very first problem on the practice final that has a non-homogeneous heat equation, that source term might have more than one non-zero term in its eigenfunction expansion. So what I showed you in the practice problem, where you have, it turns out you only have a couple of ODEs that might produce a non-zero solution, you might have a little bit more. But the process will still be the same as what you saw there. All right. Other questions? One thing to keep in mind, since I've been letting you all turn in homework whenever, again, make sure that by Thursday finals week, everything is in. It'd be very difficult to take into account anything that comes in later than that, due to a grading deadline. But the way Canvas works is the homework portion of your grade is an average of all homeworks that have been graded so far. So, like, okay, right, so far we've had 9 assignments total, 2 get dropped. Let's suppose you turned in, let's say, 3 assignments, and let's say those grades are good. If you don't do anything else, though, so right now it shows you having a high average, assuming everything else is good. But if that's all you turn in, then by the time you determine your final grade, you're going to get 4 zeros in there. That's going to drop your homework grade because those were never turned in. So make sure you take it into account that as far as if you look at how you're doing in Canvas, that's just grade in progress. But there's a presumption that you continue turning in grades that high. And yes, the lowest 2 homeworks get dropped. But that means make sure you got 7 grades in there. Or you might have an unpleasant surprise for your overall grade. I did have a situation where someone, I mean, homework doesn't count very much. Well, let me refresh my memory here. The grade breakdown. Okay, so the tests, 2 tests and final, combined are 70% of the grade. So that means that each homework assignment that counts is a little more than 4% of your overall grade. So if you, okay, so aside from the 2 that get dropped, if there are more that are not in, then it takes 3 of those to drop you a whole other grade. So I just don't want any unpleasant surprises if someone thinks that you're doing great and all of a sudden it comes to the end and you're like, what happened? Well, you didn't turn in homework. So, and I know there's still some homeworks I have yet to grade. Well, okay. 1, 2, 3. Okay, I only have 3 ungraded assignments in total. That's just individual assignments. And if I take a look at where things are at, yeah, there's and there some of you have turned in a number of assignments, so that's good. But there's a lot of red and pink in the grade book, which is a bad sign. So now, and the thing is, what I consider doing is like, well, if something hasn't been turned in to this point, like should I just fill in a 0 until you turn it in? But then that's going to make your grade artificially low. So I chose not to do that. I didn't want to freak people out either. It's like, what, 0? Because that's really not accurate. But so it's not a problem at this moment if there's holes in your grades, but make sure you fill them. And you still have time to do that, but the clock is ticking. Okay. So, last chance for any questions. Yes?
And this is the last class of the...
This is the last class, so I mean, I'll be around next week, but we won't be doing this. Okay, so may you end your semester on a good note.